Okay, so it's a great pleasure to have Clifford Johnson here with us today to tell us about non-perturbative physics for JT gravity and supergravity.
Well, it's a pleasure to be here, as it were, be here, and of course, pleasure to see so many old friends and familiar names, even if I haven't met some of the people just from papers you've been on, things like that. So it's nice to meet everyone. And hopefully I'm going to tell you some things that will get you excited, if you're not already, about some of the exciting things going on in the broad context of JT gravity. I'll give some brief motivations as to why JT gravity. I suspect I don't need to go into great detail on the whys. What I'll then do is spend a bit of time motivating why it's important to understand how to calculate non-perturbative physics, and I'll explain what sense non-perturbative it means in this case. And then I will review one of the key results in this endeavor, which is the observation by Saad, Shenker, and Stanford last year, that there's a way of capturing, at least perturbatively, a correspondence between JT gravity and a double-scaled matrix model. And that was extended quite beautifully by Stanford and Witten a couple of months later, and I'll try and explain what that extension is. Having done that, then I'll need to tell you along the way, because it's an old bit of technology that many of you young hotshots don't know, which is the whole business of the double-scaled matrix models themselves. And then I'm going to tell you that if you scrabble around in the old toolbox from long ago, there are some really useful tools that haven't been used very much until recently that you can bring to this game that then give you access to non-perturbative physics. And that's been the subject of a number of papers of mine in recent times, constructing and teasing out some of these non-perturbative results, not just in some formal sense, but in an explicit way that allows you to answer some of the questions that have been asked about non-perturbative physics. Most recently, there's been some low temperature results I'll try and talk about as well. And then I'll summarize and anticipate some, at least with some remarks, some work that I have coming out with a student of mine, Felipe Rousseau, in the coming weeks, hopefully. Okay, so that's the roadmap. So motivations, JT gravity. Well, the key point is that it lies at the intersection of a very busy landscape of ideas that's very exciting, each exciting in their own way. And then additionally, then you have JT gravity giving you nice intersections between these ideas. So a lot of the things that people like to keep in mind with JT gravity is the relationship to higher dimensional black holes. And indeed, that's a good one to hang on to. And a lot of the results that you get should pertain to that story. In particular, the picture where we have, for an extremal t equals 0, say Rajneeshpuram black hole, we have that the horizon geometry is ADS2 cross S2, and there's some sense in which you want to go away from t equals 0, at least perturb away from there, so small temperature but non-zero. And what you might imagine is that somehow you go away from ADS2 in some way, and then there should be some other dynamics that keeps track of how much you're away from the finite temperature. And that is one way of keeping track of that, is to think in terms of how far away is this S2 from the extremal S2, or if you like, how far away is the say the area of that S2, which would be the extremal entropy, how much of that is now the non-extremal stuff. And there's a scalar that keeps track of that in some sort of sense in which you've done an S-wave type deformation. And then how do you capture all of that dynamics? And in some ways, one way of thinking about JT gravity then, it is that it is precisely the dynamics of this two-dimensional gravity with this scalar coupled in some way, capturing this t equals 0, t near 0 physics. And I'll tell you about more of that in a moment. It has two-dimensional black holes in its own right, and there's a very rich story there. And of course, you may have heard a lot about JT gravity in that context, because if you were to couple that those two-dimensional black holes, that JT gravity theory, to some external sector, you could have, for example, somewhere for the radiation to go, a heat bath for the radiation of the black hole to go into, and that would be a nice context for studying the black hole information puzzle. And indeed, a lot of the work that has been talked about recently with regard to, for example, constructing the page curve is in that context. You see JT gravity featured. I won't be saying anything about that, although, as it was pointed out by others in a seminar I was giving on this same stuff, a lot of the diagrams you draw end up looking rather the same. Then there's a whole story involving black holes in any dimension as chaotic objects. And there's that beautiful story of Shenker, Stanford, and Maldaceno, I think, of bounds on chaos coming from gravity. And that's where, for example, SYK comes in, Kataev suggesting that because this very interesting quantum mechanics, which we now call the SYK model, saturates the bound maybe secretly as a theory of gravity, and indeed then it becomes the low energy dual of JT gravity. And so that's another nice motivation. It's also a theory of quantum gravity in its own right, and whenever we see one of those, we should jump on it and try and understand as much as we can, because it might teach us about quantum gravity elsewhere. And then another very exciting connection, which is the one I'll spend some time on, is the random matrix model connection. And of course, a nice thing about that is there's in literature that has nothing to do with black holes, there are well-known connections between random matrix dynamics and quantum chaos. And so in some ways, this is a sort of nice circle of ideas connected through JT gravity in an interesting and exciting way. There's more I could say about this connection as well, but I think in view of time, I'm going to move on. But for those of you who don't know, you can really have genuine conversations about other interesting pieces of physics that are of interest in quantum gravity and beyond, but also not in quantum gravity, through the SYK dual, and through the fact that you can literally build these kinds of models in the laboratory. There's a real straight-faced conversation you can have about doing quantum gravity in the laboratory via some of these connections. But that's for another story. That's for another time. So JT gravity, then, very quickly, one slide on the action. I'll have this picture, and let's talk about some of the various players. So there's the phi I was telling you about, that scalar coupled in this very simple multiplicative way to the Ricci scalar, and there's an associated boundary term, and there's an Einstein-Hilbert term with the appropriate boundary term as well. As you know, in 2 dimensions, gravity has no dynamics of its own, and so we have just a counting of topology through the Euler characteristic, and that I'll denote as follows: counting the number of handles with G, boundaries with B, crosscaps with C, crosscaps allowing for the possibility of unorientable surfaces or spacetimes, that those will pertain to JT gravity models that do not have time reversal, that have time reversal invariance. And so S naught is, as I alluded to earlier, S naught is the extremal area divided by 4G, and you can just think of that as a coupling in the 2-dimensional model, but in the sense that I talked about, in the high dimensional sense that I talked about, that's one way of thinking about its origins. And I'll say more about it in a moment. The key point then is that the dynamics is through the scalar. It happens on the boundary, integrating out the scalar imposes that this thing is locally ADS2, as we were hoping, And then there's some dynamics on the boundary. The boundary dynamics then famously turns into this Schwarzian type action. In other words, you have some ADS2 type geometry in the bulk. Instead of going all the way out to the boundary at infinity, you have some boundary, this yellow line, some finite distance. All that you have is that it is a fixed length, beta. Beta would be the inverse temperature. And I should have said that the action and everything we're doing today will be Euclidean. And finite temperature then corresponds to having some beta equals 1 over t. And you can see quite nicely if t is 0, beta, that length is infinite. That corresponds to being at the infinite length boundary of ADS2. And if you're in the interior, then it is finite. And so that's rather nice. And here's if you don't know the literature, these papers, among others, help fill in the details of this story, this action, and the resulting partition function I'll write down in a moment. The key point is then the dynamics is simply, given that this thing has length beta, it's allowed otherwise to fluctuate, and it fluctuates with this Schwarzian action. And that action has a long history, and the reason it appears is interesting, and there's just no time to talk about all of that. So we'll take that as input. If you were to go ahead and compute the partition function of the theory, it turns out to be this as a function of beta. And I will cheekily write this coupling e to the s naught that is in front of it. I will cheekily write it, or its inverse, as h bar. And we will see shortly that that h bar actually is h bar of an associated theory that I will talk about in a moment. Mostly, the discussion will be talking about spectral densities obtained by simply Laplace transforming the partition function in this way. And this famous sinh root e type function is what you get for ordinary JT gravity. Let me also just point out this power e to the s naught simply comes from the fact that we are working at disk order in at leading order. And so I just have b equals 1 and g and c equals 0. And so you see then that I have e to the s naught in front of the action. One of the things we'll be discussing is what happens if you have other topology, and moreover, beyond the topological expansion. Okay, going back to where we were, there's an analogous story for various other variants of JT gravity. The primary variant I will talk about classically will look like this, JT supergravity. You can refer to this paper for more details of its origins and the analogous computations. And the key differences for us will be that the spectral density is a hyperbolic cosine of root e divided by root e, and some other numbers that we won't need to worry about so much. That functional form is the key thing. So I'll talk about JT, and I'll talk about super JT, and I will go into more details about the differences and similarities of these various models in a moment. But a lot of the discussion beyond the motivations we had right at the beginning speaks to going beyond just the disk. So notationally, I'll use this to denote the disk level sometimes. Instead of this, I'll write just this sort of trumpet-shaped thing. Not a very good trumpet, but the trumpet is meant to denote that local ADS2 hyperbolic geometry and then some boundary. So that then we can also ask, well, what happens if we have something that has handles, has some higher topology, has some cross caps, etc. So we might ask why we would be interested in such things. And the quick answer, one of the quick answers is simply, well, this is where we came in some ways. If we're going to diagnose certain key properties of the theory, we need to study diagrams other than just this thing. For example, if I were trying to understand chaotic aspects of the spectrum, I need to look at correlators between parts of the spectrum. So I need to look at a two-point function of z, and diagrammatically that'll include things like this, as well as things like this. The gravity will tell us we should also include diagrams like that, and of course then the possibility that there are corrections to all those things as well. But immediately you can see multiple boundaries is something that's extremely natural to ask questions about, and so on and so forth. Non-perturbative effects will be extremely important. And as I said also, it's a toy theory of quantum gravity, where now the splitting and joining of the entire space-time is something that should happen in quantum gravity. We should be able to study that. Let's dive a little bit deeper into what kinds of things we would hope to get access to if we were doing non-perturbative physics. If I plotted that Sinch function that I had previously, it looks something like this as a function of energy, that spectral density. And there's my Sinch function. It looks like this, and there's some analogous thing that looks something like this for the Koch root E over E type behavior as well. What are the corrections that we expect? Well, the corrections that we expect that shape will get changed around a little bit by perturbative corrections, but actually the non-perturbative physics that you need non-perturbative physics to see, for example, this developing ripple structure, the fact that the non-perturbative corrections, as I will show you in the full models, have these bumps. You will not see without non-perturbative physics. What are these bumps? These bumps are the spectrum, the discrete spectrum, right? Going back to the four-dimensional picture, for example, we have black holes with finite entropy and Einstein gravity. So we have a discrete spectrum for these black holes, one of the central lessons of quantum gravity. Where is that discrete spectrum in this story? We're seeing that average this discrete spectrum here. So a typical black hole would have some peaks, so not peaks, some delta functions telling us what the spectrum is. An ensemble of black holes, which is what we're essentially looking at here. We're looking at averages over the spectrum, and so this gets smeared out, and that's what the spectral density is in effect telling you if you want to talk about the higher dimensional meaning of this. And so being able to get access to the full non-perturbative physics, and I will show you how, gives you access to that discrete spectrum, or at least the average discrete spectrum by computing this. So that's what the Schwarzian and the fully corrected Schwarzian physics will get you. There are other things that you might want to ask about. For example, as I said, if we're interested in this as a model of the quantum chaotic behavior of the physics, we should compute various diagnostics of that. And the most famous one is the spectral form factor, which is essentially an analytic continuation of the two-point function of the partition function. This T here then represents how long you wait for the spectrum to settle down after you jiggle the system and see how the chaos allows that spectrum to settle down. And the spectral form factor typically is in three major movements. You have this sort of decaying part, the slope, and then there's a dip, and then it goes up a ramp, and then it settles down at late times to a plateau. All of these features carry interesting signatures of the kind of system that you're talking about. How they connect together is something that you need the full physics to compute, and in particular, the ramp and its transition into the plateau and the plateau itself. Those are all non-perturbative features that you can't get in perturbation theory. And so we need to know how to do that, and I'll show you how to do that. And then finally, you might also ask about the full low temperature dynamics of the black hole. The usual low temperature dynamics that we do when we do semi-classical black hole physics looks something like this. We write down F as minus 1 over T times the action. Sorry, 1 over T times the action. And the action we usually do, although we don't usually write it, the action we usually have, that's really there's really implicitly an averaging there, which we can get away with, which we typically get away with at large enough temperatures. We go ahead and it's essentially correct. There's some saddle which dominates the action, and we work with that. It's the big black hole solution. We write down Euclideanized Schwarzschild or something like that. We compute the energy, and if we did that with our partition function from the Schwarzian, we would get something that looked like this for the entropy, for example. And there's some nice things. We get that by construction. We get the expected linear dependence in time, but we also get a disaster if we go to low enough temperatures. The entropy diverges moreover negatively for low enough temperatures. So there's a sense in which something broke down, and what broke down is the fact that we were using the wrong free energy at low energies. You shouldn't be using the log of the average. You should be using the average of the log. So the question is, how do we compute this? And as we'll see from results, when I compute the non-perturbative results for spectra, etc., of these JT gravity models, you'll see that there are huge non-perturbative effects, very important non-perturbative effects. So you can't compute this if you don't know the full non-perturbative story. And so I will show you, at least in a special limit, how I can analytically get some nice controlled results using that non-perturbative description.
Clifford,
yeah.
Okay, do you need to use replica? Just you're probably going to talk about that. But,
yeah.
Just to preview.
You don't need to. I suspect once you know what matrix model you're working with, I suspect there's a better computation than the one I will quickly tell you about, where you go and you explicitly compute the free energy in the full matrix model before double scaling, and then take the double scaling limit and do everything nice and carefully. And in principle, you don't need the replica trick to do that. In fact, there's a nice, if you like, preliminary study of this sort by Okoyama, I think, in a paper last month. But what I will do here, because the system screams that it ought to be possible, is a replica computation where you do have some of this under control, and it's kind of a replica plus double scaling computation, all wrapped up together in a nice way, which gets me the answer in a limit. And it would be nice to do more than just that ultra low temperature limit.
Okay.
But yes, indeed, replica one way of doing this, inspired, for example, by what people have been doing in condensed matter for umpteen years, is to use the replica trick. In this case, the replica trick involves including various kinds of wormhole geometries, and in a special limit that I probably won't get to in great detail, there's a dominance by a particular kind of replica wormhole at ultra low temperatures that will readily get me this answer. So I'm giving you the answer knowing that I might not get to the details. And the key thing is rather nice here, is that all of this physics is controlled by one particular number. And it's a number I can compute non-perturbatively. And it is the spectral density at zero energy, which is a curious thing that shows up when you do the non-perturbative corrections. And you can compute everything in those, the free energy. So think of this as ultra low temperature. So in other words, it's exponentially small, the exponential there being e to the s naught. So this is way low temperature than you normally get in semi-classical discussions of black hole thermodynamics. Nevertheless, it mirrors quite nicely ideas of Preskill et al. Going back to 91, where they noticed that near extremal black holes ought to have some bottom to the low temperature physics that is controlled by the lowest energy state of the black hole. You have this discrete energy. I'm emitting quanta if my temperature is of order the size of those quanta, that thermodynamics should break down. That's the discussion that they initiated there. I can show in this model that indeed this phi 0 is precisely that lowest, that essentially that first peak that you get in the spectrum. It is the gap. And so in some sense, this is a first principles realization of those ideas from way back, where you can actually compute. So I'll say more about that later on. Anyway, it's already 12:30, and I'm still in the introduction. So I better tell you something else. Although this is still an introduction, but let's tell you. So matrix models. So the key idea then that I wanted to talk about next is Saad, Shenker, and Stanford. Henceforth, I'll say triple S, because the S's keep tripping me up. And they talk about Hermitian matrix models and the double scaling limit. Some sort of, those are words, and many of you might not know what that means, because everyone used those words back in the late 80s, early 90s, and then we moved on to other things. So let me remind you what all of that is. And essentially what you have is some model of a large n, n by n Hermitian matrix called M. It looks like this. There's some if you like, it's just a matrix, quantum mechanics. And then there's a trace, sorry, some potential V of M. This goes way back. This has an ancient history. If I didn't have, for example, this m to the 4 piece, I just had this m squared. This is Wigner's Gaussian ensemble of random nuclei, where he was trying to understand the typical behavior of the spectrum of nuclear physics. We can, though, put on our field theory hats and say, oh well, I could have some n to some power, and think of that as some vertex. And then maybe it's a pretend model of QCD motivated by thoughts of 't Hooft. We would go, well, what we could do is work at large n and draw Feynman diagrams. Feynman diagrams here would propagate the matrices, the matrix indices, if you like. So I draw ribbon diagrams. This m squared would give us the propagator, and n to the 4 would give us a quartic vertex. So I've drawn a couple of diagrams here. Notice, for example, that that'll give you a power counting in n when I build diagrams. Inverting to get the propagator will give me a 1 over n, and then vertex has an n and a g. So I can actually work out the powers of n, these diagrams. It's a fun thing to do. What you notice, to have taught us, there's an organization in terms of powers of n. Leading, you can draw on the plane or the sphere. There's subleading ones that can be drawn on the torus, and so on and so forth. So the large n expansion captures topology, which is rather nice. And there's a sense then, well, various communities get excited about this, including the string theory community way back in the olden days, the string theory and quantum gravity community, because there's a sense in which maybe you could capture the sum over random surfaces, changing their topology according to some rules, but you need smooth surfaces, right? If I were to decorate these diagrams as follows, for every face, I draw a vertex, and for every propagator, I draw okay, let me put the vertex there, something like that. And then I have identifications that ends up identifying this with that. What I've done is I've tessellated the sphere that I could draw this on with in the crudest possible way by basically tessellating it with a single square. So that's a bit rough from the point of view of drawing a good smooth sphere. But I could do better. Larger diagrams involving more vertices and more loops will get me more squares, and I can imagine doing better and better and better as I tessellate the surface. And in fact, if I could find a limit where I pick out the surfaces where the number of squares in fact diverges, and tune things so that I can extract the physics for those sorts of diagrams, then in fact I could capture the smooth physics of random surfaces that are good approximations, better and better approximations to being smooth spheres, and similarly at subleading order. And that is what the double scaling limit is. And it turns out essentially that you do this by simply tuning this G, which I kept free here, to a critical point where you get that divergence. And there's a whole beautifully organized way of doing that, going back to Brezin, Kazakov, Douglas, Shenker, and Gross and McDowell. And I don't have time to tell you all of that technology, except to talk about some key pieces. Oh, that was just another diagram showing you that same idea. Except to show you some key pieces which come out if you dive a little bit more deeply into solving the model. If I diagonalize M with a unitary in this way, so I work with the diagonal, the eigenvalues E tilde, the energy eigenvalues like that. The cost of doing that diagonalization is a determinant, which actually is famous. The Van der Mon determinant looks like that. And then I have a sum that looks like that. How do I think about this model? I think about this model as follows. I have the potential that I wrote down, V, that naive potential. What is it doing? It's confining those energies. It's pushing them this way into the middle. But I have a repulsion between them coming from the Van der Mon that's pushing them out. And you can imagine that it shouldn't be too hard to imagine that you should be able to find some solution representing a sort of droplet that forms, balancing those two phenomena. This Dyson gas and this droplet in the Dyson gas, then, when you tune along the lines that I talked about before to get to that critical physics at large N, what you're actually doing is you're zooming in on an endpoint of the spectral density in this way. And you're picking all the universal physics ends up being arising in this endpoint like that. An example of this is that Gaussian case, going back to Wigner. If I just had the Gaussian case, you have the famous Wigner semicircle law that looks like this. I've written it, parameterized it in a way where I've put the center away from zero. It's usually put around zero in most presentations. And you can see then if I work in the neighborhood of the endpoint, E tilde goes to is 0 plus some small e, then I get this e to the half behavior. This e to the half behavior, I'm going to say, is a prototype for a much more general story. And in fact, that general story is essentially e to the k minus a half. This goes back to what Kazakov in the old days called the multicritical models. And that comes from working with more general V and finding those critical points I talked about. So there's an e to the k minus a half type behavior. You can extract a class of models of this form. They were very exciting in the early days because they were, in fact, you could think of them as string theory models called minimal strings. They weren't called minimal strings in those days, but they later got called that by Seiberg. And they actually were 2, 2k plus 1 in the PQ conformal field theory classification. Those conformal field theories coupled to 2D quantum gravity, or Liouville theory, if you prefer. So there's a whole bunch of them, and they're interesting, and you can capture them by matrix models. And one of the excitements from those days was that you capture not only, through that topological expansion I told you, you capture not only the perturbation theory of splitting and joining of world sheets, etc., but you also capture non-perturbative physics through a family of ordinary differential equations. So essentially you have an ODE, and I'll show you some later. You have an ordinary differential equation that comes out of the matrix model. And if you look at its perturbative solutions, and expand about this perturbative solutions, that corresponds to doing world sheet perturbation theory, those different diagrams of different topology. But then those differential equations have fully non-perturbative solutions as well, and those capture the non-perturbative physics. And I'll show you how that works a little bit later on. So JT gravity isn't one of these models, but there's a sense in which you can engineer JT gravity by putting together an infinite number of these models in a certain way. And make sense of it in not just a formal way, and that's where we're going. And this builds on, there was a suggestion in Triple S they already realized by looking at the spectral density that it in some sense, could be thought of as a limit of a minimal string model. And so they had that suggestion in there already. But the details are quite a bit more rich than that, I would say. That's what I've been unearthing in some of these models. An early adopter of some of those ideas, predating my work, would be the December paper of Okoyama and Sakai. Okay, so where do we see the first signs of that construction I was telling you about? Well, if we expand the cinch function in this way and just look at it, we can see something rather nice. It's made up in some sense that I'll make precise, it's made up of these sort of signature e to the k minus a half type behaviors. And that's sort of interesting. There's the Gaussian model, and there are the higher k models, if you like. These coefficients then, in some sense, are telling us that they're present in some particular mixture. And I need to show you how to construct that mixture, and then how to, given that mixture, put it together in a way that gets not just the perturbative physics. And there's something beautiful about the way those models are organized, going back to the old 90s work, that tells you that that mixture is actually rather straightforward to do once you realize that's what you're doing. There's a linearity which tells you how to build the models, although the whole thing itself is horribly nonlinear, and I'll explain how that works in a moment. Similarly, you can do similar things for the supergravity models, and that's where I'll focus a lot of my work, because in some that I'm describing here, because in some sense the non-perturbative physics is much easier to describe in a 1-hour talk than the JT case. So, as I said, we want to understand indeed the perturbative expansion, which I'll write something like this. But I want also to go beyond. I want the and beyond aspect of it. I want to be able to have non-perturbative physics. So what Triple S did is essentially they showed us, they led the way in showing that all of this is there in a matrix model. But intrinsically, their construction is perturbative, although in both Triple S and SW, they do make some important non-perturbative observations, but the core thing is perturbative. And that's because they write recursion relations. You can write down the structure of the matrix model you're interested in without knowing the potential explicitly, and you can write down the recursion relations. You can write down what the recursion relations become in the double scaling limit. And then they tell you that if you know the spectral density at order G minus 1, you can use the recursion relation to compute it at G. So given that the Schwartzian gives us the rho 0 from a completely different method, nothing to do with matrix models, you essentially define the matrix model through its recursion relations and knowledge of this. And that's essentially the logic. It's a beautiful construction, and should not be it should not be underestimated just how powerful that is, and how non-trivial it was to check that this is true, right? For you have to, on the JT side, you have to at arbitrary genus and number of crosscaps, etc. You have to compute this on the gravity side, and then you have to check that what you get matches what you get from the recursion relations on the matrix model side, and that's highly non-trivial, and that's what Triple S did in their paper, and then for more general models, SW. Along the way, you use some beautiful mathematics connecting aspects of the moduli space of Riemann surfaces that you need to be including in the path integral, and properties of matrix models. So work of Mirzakhani and Ardorentin. So it's lovely stuff that I don't have time to tell you about, but it's essential. And we're not going to use any of that, but I need to pay tribute to how remarkable that step was.
Clifford?
Yes.
Can I ask you a quick question about that stuff? So just to orient myself, in the old matrix model, just the multicritical models, was there a topological recursion in the same sense? Or do you get it just in the limit?
No, it was there, and in fact, there are various cousins of what we would now call the Mirzakhani type relations, done quite generally. But there were versions of that going back to, for example, the work that was used in things like the Witten-Kontsevich model and things like that, which I'm sure you remember, right? There were lots of recursion relations that come from the matrix model, telling you about, for example, relationships between insertions of operators on Riemann surfaces of different genus and things like that. Those are all in that same class of things that you can extract from the matrix model if you were interested in that. Mostly studied for topological gravity, but was there for any of those models, but not really explored as much in their own right mathematically, except in the topological case. But then later, people like, well, the authors I just mentioned, Einard et al., were talking about
that's right.
how to write the later discoveries of Mirzakhani back in terms of matrix model physics.
Yeah.
Okay.
Yeah. Just one comment. I mean, the nice thing about this recursion relation is that, you know, these multi-boundary surfaces sort of have to be included. So,
yes.
And that was still true back in the day, presumably.
It was still true, but I don't think people were, well, okay. I think there was less work on it. But again, I should be careful because there's just so much literature. So many things have been rediscovered, sometimes to the frustration of some of us, and so many things have been forgotten. So the thing that was, from the string theory point of view, perhaps less well developed, which I'll talk about right now in a moment, are indeed the multi-boundary stuff, which in those days would have been correlators of multiple loops. That's a weird looking diagram. You'll see what I mean in a moment. Correlators of multiple, that's as opposed to this, which would be correlations of operators.
Yeah, I think I get it.
all the diagrams look the same, right? It's like the D-brain days where everybody's diagrams basically were this. Yeah, there's a lot of stuff which goes back, for example, to multi correlations of what we call macroscopic loops, which you then later on think of as boundaries landing on D-branes and things like that, for which in some ways the Mirzakhani, etc. technology was speaking of more directly, where you have Riemann surfaces with arbitrary boundaries. I think a lot of the stuff from the old days, those boundaries were shrunk to points, and then there'd be operator insertions. Yeah. Okay. So anyway, a lot of beautiful history, a lot of forgotten things. Here's some forgotten things. So there's another method that I want to tell you about, and it's the core of what I've been thinking about recently. And that is that this row that we've been talking about, the full row, is in fact the spectral density of an associated one-dimensional system that it comes out of the matrix model, at least for a certain class of matrix models, the one-cut double-scale matrix models of the kind that seem relevant here. Out comes also a quantum mechanical system. All we need to know from the perspective of today is that there's some parameter x that I will fail to fully tell you where it comes from unless you press me in questions, and some function u of x. What you need to know, all you need to know essentially, is that they have their origins in the matrix model, double scaling, after double scaling. Let me tell you a little bit more about X. X is essentially the index, starts out life as the index that everybody carries going from 1 to n, where n is the size of the matrix. Well, actually it's index divided by n. And then essentially as n goes to infinity, X becomes a continuous variable. There are various objects then in the matrix model, essentially coming from writing everything in terms of an orthogonal polynomial basis, which is fairly standard in solving these sorts of problems. And there's, for example, there are recursion relations between the orthogonal polynomials, and there are families of them sorry, there's a whole family of n of them that come out, coefficients that essentially you can decompose the whole problem in terms of alternatively, as an alternative way of doing things. And these become functions a of x later on. And there's a scaling piece of a of x that becomes this thing u. So I don't know if that was helpful, but it at least tells you that these things are not made up. They come from the matrix model. But the key point is as follows, that out of this model, out of this arises this thing. This thing is a genuine Schrodinger Hamiltonian H. That little h bar then will turn out to be the h bar that we want, the thing I was talking about earlier when I match this to JT gravity. And that potential u of x satisfies some differential equation that comes from the matrix model itself. And it is a nonlinear ordinary differential equation, which in the old days we called the string equation. And I'll give you some examples of it shortly. The point is that if you know what u is, you can in principle solve for the spectrum of H. And the way u arises will give some nice properties to that spectrum, which will make it very nice for studying JT gravity, it'll turn out. And essentially you extract this object, you extract this object by essentially looking at the particle density and integrating x over some range. It goes from -infinity to some parameter I'll call mu. Talk a bit about that in a minute. And if you do that, that's sort of projecting out part of the particle density, if you like, and grabbing that and calling that thing rho of E. That turns out to be the thing we're interested in. So that looks a little bit magical. So let me unpack it a little bit for you. So classically, what happens, for example, yikes, it's 12:51. Okay. Classically, what happens, for example, is as follows. As h bar goes to 0, I should arrive at some sort of classical physics, and that will, the leading piece in h bar goes to 0 should be that disk physics we're interested in. What you'll see is that there's some piece of u left over, which I'll call u0. Rho reduces to its disk level piece, and up to a normalization, which I'll choose based on, for example, how the wave functions are normalized. I will end up with some piece that looks like this. There's the disk piece telling me I'm on the disk, but the key thing is I have this function to integrate. And you can see that the pieces are as follows. So I've color coded it so you can see what's going on. If I'm asking at some energy E, if I'm at some energy E, this is the potential, then if I was doing in the sense of some sort of WKB analysis, I would simply look at the leading, I would look at the leading piece, the piece where this square root is giving me something real. I would integrate over that range, and I would get some number. If I do that over all the e's, I will then construct some function, and that will turn out to be rho, or I should say rho 0 of E. So that's what the leading classical spectral density looks like pictorially. And there's a way of relating this to some of the old matrix model technology. There's a way of relating this to, for example, the spectral analysis you might do of the large N construction in matrix model physics involving things like resolvents, etc. We'll take this essentially as our guide for how things look classically from now on. And I will come back to that formula in a moment. More generally, though, if I want to do the full physics, of course, I'm not just doing the classical physics. I will have genuine wave functions at some energy at that energy E, right? And those wave functions will also know about that region going into, if you like, the classically forbidden region. And so that's why that integral extends over all of that, including all of that physics coming from that stuff. That'll be the quantum physics going beyond just leading it in H bar. Also, the function U itself will get modified. As I will show you, there'll be some change to U that actually, for some of the physics we're talking about, will look something like that. Okay, so that's the sort of classical story and how it corrects into the quantum story. I should say, very crucially, another reason this picture is extremely nice is because it tells you intuitively a lot of what's going on with the beyond classical physics. It'll tell you intuitively very important things about the potential non-perturbative structure of the theory, because you can essentially just look and see what the wave functions are doing in this kind of potential. So that's all of the sort of technology that, in some sense, SSS doesn't have in their construction. They're not thinking about double scale matrix models in this way. So for diagnosing some of the things we want to get at, like the non-perturbative physics, this picture is going to be extremely powerful for us. And so these are the key tools. So the challenge then is to find the correct U, given that SSS exists and have told us what their matrix model is. What is the U that they implicitly have? They don't have it because they're not working in those terms, but there's some U that would perturbatively give you the same physics that they have, but then non-perturbatively would get you the rest of the story. And it depends in general then which JT gravity you're talking about, and then it'll then depend upon what kind of matrix model you have. And the key message then is that you should consider many more kinds of matrix model than just Hermitian matrix models with the naive potential that you might write down. And it leads you also to study and control more kinds of JT gravity. Okay, in view of the time, I'm going to tell you a couple more key organizational features of how this technology works, and then I'm going to skip ahead to quickly telling you how to build all of this and give you some results. I think I started maybe around 8 minutes past.
Yeah, Clifford, you shouldn't worry about your time. I mean, we're half an hour earlier than usual, so all of us are fine on time. So you should worry about your own time.
Right. Yeah, I have a class at 2, but I more or less know what I'm going to talk about. So, but I'll hopefully, don't worry, I'm not going to go till 2. But it'll allow me to give you a little bit more detail then. Good. Okay, and we can have a nice discussion as well. So maybe shooting at 1:30 or so to close everything out. That sounds good. Okay, good. Okay, another piece of old technology, as I mentioned before, was what we call macroscopic loops. And you might then ask, again, it's a nice natural quantum gravity question from the old days. And in some sense, it's one of the few observables you have. If I have the quantum mechanically fluctuating random surfaces, what can I hold fixed? What's a good observable? And one of the things they considered in some nice work going back to Banks, Douglas, Seiberg, and Shenker were macroscopic loops. What if can I, in the matrix model, cut a hole of some length, which they called L, but I'm going to call beta for obvious reasons, I hope. But then otherwise allow the matrix model to compute the sum over random surfaces. And you can do that, and it turns out the answer looks like this in the quantum mechanics. And in fact, the quantum mechanics, the focus on the quantum mechanics that I just described, that comes out of the matrix model, goes back to these authors and Gross and Migdal, who very readily began to recognize the importance of that Hamiltonian H. So it looks like this, and there's a lot to be said. One way of thinking about this is that it is a trace over e to the minus beta h, but with some projector, and that projector is essentially that funny integral as I've been telling you about that we already saw, pulls out the spectral density. let's have a closer look. I'm sometimes going to denote this like this. And we can massage this a little bit. We can take this prescription and we can insert a complete set of wave functions, for example, just sticking in a complete set of wave functions here, integrate over all possibilities, and then use the fact that h psi is e psi to do the next step, which would look something like that. And then we recognize, this is what I would call the wave function psi and psi star. And so this is our friend. Let me remove that junk that I just put there in the way. This is what I talked about in the first place. This then is the partition function z I started with, or the expectation value of one loop that I started with previously. And now we see that it is also the Laplace transform of some spectral density defined this way. And we go, oh, okay, now we see that this loop really deserves to be identified. This picture deserves to be identified, at least structurally, with what we had for JT gravity. If we could find the right U to go into this H that would give us JT gravity, then this would be the JT gravity partition function. That's the logic. So the question is, what's the U? And I'll get to that in a moment. But let me also show that once you have this technology, there's much more you can do. Already developed in that early paper of Banks et al. Was the technology for describing how to compute higher order correlators of Z, for example. Here's two Z's, the connected piece ends up looking like this. You essentially sprinkle powers of e to the minus beta h and this projector p in various ways. And there's a very nice technology for doing that. This would give you this. There's a nice way of writing it, actually, which I first learned of in that paper of Okoyama Sakai that I talked about, where you just sort of expand this out. The pieces involving one p essentially look like then a copy of z of the partition function at the sum of the betas, and then which is manifestly positive, and then you have this subtraction here. And the reason this is nice is because if I were to go ahead and prepare this for being the partition function, sorry, the 2-point function for computing the spectral form factor, this piece turns out to be the ramp. And then this subtraction is sort of going away from the ramp. In other words, you have the ramp, which is positive asymptotically, and then there's some subtraction away from it at earlier times, and that's precisely what this piece is controlling. And then the rest goes off to make the what Mark will agree with me should be called the saxophone shape of the of the spectral form factor function. Okay, so that's rather nice organization. The reason I bring this up is because it's quite natural also to think about higher powers of Z. This is in preparation for perhaps the replica type computation that Moshe anticipated. And one nice observation, which I talk about in my paper in August, is how higher powers of n, the nth power of Z, higher powers of Z have a nice organization. If I'm working at low temperature, the leading low temperature piece is always this leading piece. That's like the very late time piece in the spectral form factor. It's controlled by that, the ramp. And so in general, this is the piece. The n dependence is extremely simple, and that'll turn out to be rather nice if you're doing a replica trick. The other stuff is there, but it's subleading. The other stuff looks like this. And what you can think of it as is, in some sense, the physics is dominated by some distinguished type of replica wormhole. There's sort of n of these guys that essentially look like you're working with, you can think of it as a partition function at n beta in some ways. That one power of beta versus more powers of beta in there is what makes it lead at low t. So if I can track this and all the non-perturbative physics it drags with it at low temperature, I can get a piece of the low temperature free energy via the replica trick. So if I don't get to that, this is the sort of key for organizing that computation. And again, it's all the matrix model it's all the matrix model technology. One last thing to say then is that normally what we'll see in the full model, I'm building this thing out of tracing over Z, and I know the spectrum of H, and so I build everything, and there's lots of integrals over wave functions. I need to know those wave functions explicitly. In general, I will only know those wave functions numerically because it'll be a highly nonlinear potential, a highly nonlinear problem, but I can extract that in some very well-controlled way and get answers out for the correlators. In the limit where I do the replica trick, I will actually be able to write down the wave functions in terms of Bessel functions and compute everything analytically and get some nice analytic results. But in general, it's a horrible nonlinear problem that requires numerics. Let me then give you a couple of examples just to show that this isn't just random magic. It's very specific magic. The full non-perturbative description, for example, of the Wigner model, that Gaussian model, gets often called the airy model. Let's have a look at it in this language. So the potential in that case is just u equals minus x. It's just this white line here. And so again, what do? I should construct the spectral problem. Well, the spectral problem is just Airy's equation, it turns out, after a change of variables, and the wave functions are just the Airy function in this way. There's some, it's kind of keeping an eye on the answer and the normalization of the answer. I've put in some normalization factor there. These are actually non-normalizable in the usual sense because they're free asymptotically. But there's a normalization that is natural by comparing to the spectral density I get on the sphere. So what happens? Well, if I just looked at let's just do that first of all. If I just look at the leading piece of the Airy function, the leading classical piece, if you like, and I do what I'm supposed to do, in these models, that parameter mu actually is 0. And you can think of that as a rule here. Mu equals 0. I'm doing stuff that's akin to JT gravity. It turns out mu equals 1 will control things that pertain to super JT gravity, and I'll explain why in a few slides. Anyway, if I just do that, I get this. And there is, from now a different perspective, that same e to the half type leading behavior. The non-perturbative physics, oh yeah, let me say this. Using that other tool that I was talking about, where I thought of this now just as doing that simple classical integral, that 1/2 pi h bar integral over that square root. I've changed variables here where instead of integral over x, I do it over u0, but essentially the logic's the same. I know this u, I stick it into that integral, and I do this integral, I get that. And in this case, that will give you the answer. So that's a nice, simple example of all of these different pieces of technology working together then. Either you look at the wave function, you do the full wave function integral, and I just looked at the classical piece and got this, or I work in this limit where I just do this integral for what turns out to be the same. There's no h bar dependence in this case for u0, and I get that. The full story then involves having a whole family of cases where u goes like minus x to the 1/k. And you can just see on general grounds, if I stick that in there, I'll get a spectral density that goes like e to the k minus 1/2. Now, I can tell you what a string equation is. In this case, for the Hermitian matrix model, the string equation looks like this. And in some sense, what I'm saying is that there's a full u of x at leading order, this is what it behaves like, but there's a more general behavior and it's controlled by a differential equation. Differential equation looks like this. There's a family of objects called the Gelfand-Dickey polynomials that are simply polynomials in U. So you have U to some power and you have derivatives of U to some power and products thereof. So it's horribly nonlinear. The leading piece in derivatives is the 2k minus 2th derivative, and the leading piece in U is U to the k. But this dotted line means that there's products of lower powers of U and its derivatives. So it's horribly nonlinear for the kth model. The kth model then looks like this equation in the box, which is to say, if I say that combination of U and its derivatives equals minus x, and I solve that differential equation, I get the full U of x. At leading order, you can see that, oh, there's an h bar in front of every derivative. If I send h bar to 0, I just get U to the k equals minus x. And so that's the leading thing that gives me this as the classical solution. But in general, you have to solve that differential equation. This then becomes a boundary condition for that differential equation. The really nice thing is that you can put together, in a very well-defined sense, it's essentially RG flow, you can combine together many RK models. Essentially, it's like you're in the kth model where k is the highest k, and then you turn on all the others by turning on operators in that model. And it turns out the string equation for that is simply to add them together in this naive way that you would have thought was ridiculous, but it's linear. But realize that what you're doing is you're adding these things together in this nice way with these coefficients, measuring the strength of how much of each model is in there. It's linear, but you're adding together nonlinear structures, and then you're solving for U, which is a nonlinear problem. So it's not that you're taking solutions U and adding them together. You're building the equation in this linear way, and then it builds you this horribly nonlinear equation which you solve. I hope that's clear. It's that simplicity that is the key to being able to know how to build the JT partition function.
Clifford,
yes.
Can I ask? So what's so special about this specific coefficient TK that give you what you want?
I will say more about it, but from our pragmatic perspective, knowing the TKs will be knowing the recipe that gives me at tree level the cinch function that we that we get from the Schwartzian. Yeah.
No, I get that you have to choose specific TK to get to the target that you want, but I mean, why is there only one set of TK very finely tuned that has a nice interpretation?
Well, exactly. Well, there isn't. What you then find is that the freedom to have other TK should correspond to deformations of the gravity theory.
Yeah, so there is the discussion with different potential. You cover the same ground if you change the TK. Is it exactly the same freedom?
Yeah, well, what you'll have is the freedom then to have different potentials U of x, which will in principle then correspond to different JT gravity models. Mm-hmm. And then you get to explore. You get to explore what physics can I get by changing the TKs, and are there constraints on the TKs? Can I do anything or not? And so I won't get to talk about that in this paper, but actually that's something that I've been working on with Felipe Rosso, and we actually have some really nice results. You can indeed. There's some lovely work corresponding to deformations, which already have an understanding classically due to work by Witten and Maxfield and Toriachi, separate papers. You can build their examples out of TKs, and then some of the puzzles they're trying to understand there, you can ask what does the non-perturbative physics say using these methods I'm telling you about now, and get a beautiful story. You'll have to maybe ask Felipe to give you a talk on it. I don't have time to go into it here, but it's a really exciting story. We've just this weekend got some even more exciting results we're dancing about, and so it's kind of fun. Okay, but that's a great question. Okay, and just as a model of the kinds of things you can then get access to non-perturbatively, let me also stick with the airy model and go, okay, well, I can look at the full wave function. I can do the full prescription that we're supposed to do. There it is, and I can just use my airy function identities to deduce that this is the result, and you can see a nice expansion perturbatively, and then instanton type effects and oscillatory type effects that are non-perturbative, and it's all there. This is, if you like, a toy model, as already pointed out by Triple S, a toy model of what you'd like for the full story of JT, where these ripples, these bumps are telling you about the discreteness of the underlying spectrum, which you've averaged over, and so on and so forth. So our goal is to do this, but for the full JT gravity. And I should note at this point that one of the beautiful and interesting subtleties of the whole story for JT gravity is this penetration into the forbidden zone that Triple S notice and worry about rightly. Sometimes they potentially destabilize the non-perturbative definition of JT gravity via Hermitian matrix models. How do you fix that? One of the nice ways of seeing, and this goes back to my December observations where I first entered this story, this game, is that it's extremely natural to diagnose where that comes from in this picture with the potential U, because you can simply see that it comes from integrating over wave functions at negative energy that still nevertheless have a tail that penetrates into this region you're integrating. Even though you integrate only up to there, you have this exponential tail from those guys coming in. It immediately tells you how to fix the problem. Don't have this region, basically. And so are there models for which you have this kind of physics which agrees with the perturbative physics at higher energies, but at lower energies have better behavior down here? And in some ways, that's the key to understanding a lot of the message of some of my earlier papers, which is that there are models, there are other minimal models that don't have this sort of physics, but agree up there. And if you put those together in the right way, you can, if you like, come up with a nice, well-behaved, non-perturbative regularization of JT gravity that doesn't have this stuff. And or if you put them together in a different way, you can build super JT gravity models as well, which at the outset have a nicer non-perturbative physics. Let me very briefly tell you where those minimal models come from, and then I'm going to put it all together, give you some results, and then tell you what you get out of it. So there's a different kind of minimal model available, which again goes back to the late 80s, early 90s, and in fact goes back to some of the work that I was doing in my thesis work way back in those ancient times. One of the key things that we saw, so this isn't, of course, the language it was described in those days. This is sort of my updating of it, adapting it to the current context. We saw, for example, in JT supergravity, there's this 1/√E type behavior that isn't captured by the kinds of minimal models we were just talking about. So where does that come from? And you can see, just looking at my integral that I was telling you about, my classical integral, if I had part of the classical physics have that function U of x is in fact 0, you can see immediately that I would have this 1/√E behavior coming out classically, controlled by now that mu. We had a 1 here in the normalization that I'm using for JT supergravity, and so mu is 1 in that case. Notice that I can also have models that have this kind of behavior, bringing this out, but if I integrate it up so that mu is 0, I actually truncate that away. And so that's the key, essentially, to tell you what's the difference at this level between using these models in JT gravity, where I don't have that 1/√E behavior, I have mu tuned to 0, versus it being 1, where I do have this type of behavior. And in some sense, then, those kinds of models, those kinds of gravity models are not so different. They come from you're doing a different projection on the matrix model. I didn't just make up that kind of behavior. This kind of behavior is possible. It goes back to complex matrix models, which have a history going back to Tim Morris back in 1990, asking, what can I do with complex matrix models that taking double scaling limits just as you would do on the Hermitian matrix models. And there's a nice story, which I don't have time to go into, except to say that you can pretty much do the kinds of things we talked about before for Hermitian matrix models, complex matrix models with a potential that looks like this. There's a natural language that then comes through the story where I do the eigenvalue diagonalization, etc. I get a van der Waals type behavior with an extra power 2 here. I get a, sorry, it's a power 2 here, but it's for lambda squared, I should say. And there's an additional piece, some extra work we did later on, where we showed you can also include a parameter called gamma, essentially a logarithmic type piece of the potential, which in the old days, the semi-old days, you recognize actually are telling you about the presence of certain d-branes in the model. In those days, we just called them open strings. And together, they build for you essentially something that looks like this. I have my measure, instead of just being d lambda, lambda minus lambda squared, it's something somewhat different. And that's actually been classified in modern terms in terms of what's called the Outland-Zernbar ensembles. And in their classification, they call that power alpha, that power beta, and that's what they are. Now, Stanford and Witten, in generalizing triple S, took the following line of reasoning. They said, well, given that triple S and JT gravity is captured by Hermitian matrix models, random Hermitian matrix ensembles, we could ask and we could classify the possible matrix models, and that's already been done. It's either the Wigner-Dyson type ensembles or it's the Outland-Zernbar ensembles. And every single one of those should define for you a type of JT gravity. And so they realized that there were a whole bunch of interesting models, including some JT supergravity models that were classified in these terms. So I'm here to tell you that actually there's some lovely work coming from double scaling complex matrix models, where a huge amount is already known about the kinds of physics that you can get, and a very lovely class of minimal model that we found that we were trying to make relevant to a different story, and turned out to be recognized as, in the string theory language, to do with type 0A string theory minimal models. But now the new connection, which I uncovered in these recent papers, was that these are also models you can use to build some of these supergravity models, defined thus through the matrix ensemble classification of this measure. Moreover, you can put them together in a different way to also give a non-perturbative definition of ordinary JT gravity, in a sense that I alluded to on the previous slide. So that's a lot to say on one slide, and there's a larger story there, and it's a very beautiful story. But let me just give you some of the key differences between these things and the minimal models, and then I'll show you some results. The double-scaled string equation that comes from these models that we discovered in those old days looks like this. And it looks rather daunting, but actually it's built out of the same objects I talked about before. So the object I had before, which was the Hermitian, which gave you the Hermitian matrix model string equation, was essentially this plus x there. And if I asked that that thing be 0, that was the Hermitian matrix model. If instead I asked that this thing satisfy this larger differential equation for some parameter that in the old days we thought was an integer only, gamma, because we thought it counted d-branes. I mean, it does count d-branes. Then you have this. Then you have the solutions give you this larger class of models. My recent observations then are that are twofold. One, gamma can be not just integer but half integer as well. It has a natural interpretation in terms of what will turn out to be these JT supergravity models. But you can also have gamma equals 0, and that will pertain to ordinary JT gravity, and then the solution that you have R equals 0 will correspond to the same high energy regime that you had previously for JT gravity, but at low energy you have an additional solution which corresponds to that U equals 0 type behavior I was telling you about. When you put those together as X varies in the picture that we've been talking about, it looks like this. That's the classical picture. And it then gets corrected when you do the full non-perturbative physics. When you solve the string equation, it gets corrected into physics like this. You then see very stark differences between the kinds of things that can happen. You have, for example, the airy model gives you this sort of thing. You get the stuff that at higher K will give you problematic non-perturbative physics because the potential goes down here and you have this negative energy stuff giving you an exponential penetration into a bad regime. You simply don't have this there. Essentially, the airy agreement, the agreement as being airy at high enough energies changes as I go to low enough energies. These airy functions actually turn into Bessel functions and give you a different, more well-behaved behavior. So, more well-defined behavior. So that's essentially the key of the better behaved non-perturbative physics that you can get. And diagrammatically, this is the sort of thing that comes out. So you can use this for JT gravity and also very naturally for super JT gravity as well. So ultimately then, this is the recipe. I either use these things for JT gravity or super JT gravity. I need to find what the TK recipe is, and off I go in order to then solve the full string equation. Having matched things at disk level, I can then get the full string, solve the full string equation to build the full potential. So typically now I have all the ingredients to give you this sort of stuff that we saw in the spectral decomposition and this sort of stuff. And I can tell you then how to build everything I need. So as I said, Okoyama and Sakai already noticed that the ordinary minimal models, if you use this combination of TKs, you'll achieve that business of deconstructing perturbatively the triple S matrix, Hermitian matrix model into minimal models. What I then recognized was that that same combination, but using the better behaved minimal models, will give you a nice non-perturbative definition of JT gravity, and that's the content of not that paper, but the December paper I talked about. You can actually integrate this whole thing up and get a nice expression for the string equation at tree level in terms of Bessel functions that looks like this. Different Bessel functions, modified Bessel functions. And then the supergravity story, this cosh root E over E, turns into a beautiful expression in terms of the minimal, this new kind of minimal models I was telling you about. You can get that nice root E behavior that way. You can use them here, as I said, and mu equals 0 will kill that 1 over root E type behavior and then give you the right coefficients for the cinch. So that's the difference between those two prescriptions. I need to solve the string equation. So I have the full non-perturbative definition now. I know how to, if I can solve that U for that U, I'm good to go. And at this point you go, well, yeah, that's fine, but I'm taking an infinite number of these things, which means I have an infinite number of derivatives in this string equation. So this is a formal problem. How can I actually solve this problem? And just for sake of illustration, I'm going to focus just on these two cases, these nice 3 JT supergravities, just for talking about the practical results. The key point is that I can actually truncate the model. The TKs, in some senses, I get to larger and larger K, get smaller and smaller. And there's a sense in which I can truncate to some high enough TK and get a good approximation. And in some sense, what happens is that I have a good enough approximation to the potential, the full potential that I need at tree level. It works at a, if I have, let's say I'm interested in a question at a given energy, that energy and below, I want everything as accurately as possible. it tells me how many TKs I need to include in order to get the accuracy I desire. And so it's a well-defined procedure that I can do in order to answer a question at any particular order in of accuracy at a given energy. And you can imagine iterating that procedure as desired. Ultimately, then it tells you what order of the differential equation you need to solve. And for way of illustration, I solved some 12th and 13th order differential equations in order to do this. And you can do it. It's a matter of letting your laptop warm up a little bit for a while, and you can do it. You can then solve for the spectrum. And actually, so here we go. So here are now some results for the JT supergravity case. And I need to make some observations for later use, which is that, well, here, this dotted line is the cosh root E over root E type behavior, the classical physics. Notice the spectacular corrections that you get from non-perturbative physics at low energy. That's important. The non-perturbative physics is extremely important, especially in understanding the low temperatures, the low energy physics. That'll translate into some of those things I already anticipated for the low temperature discussion later. And there are some other examples. There's a case where you don't get that cancellation to zero. You get some other thing happening. It's a longer story than I have time to talk about. A very nice JT supergravity result, which I'd like to, oh, you can also compute the spectral form factor. In view of the time, I'll jump away from that. This 1,2 JT supergravity I mentioned here for two really good reasons. One is that it is one that is in some ways very analogous. It's the closest analog of ordinary JT gravity in that it's not time reversal invariant. So it's a little bit more physical, if you like. And one of the things that it also shares with my non-perturbative definitions of JT gravity is that it has a non-zero, when the dust settles, the spectral density at zero energy is actually non-zero, which is rather curious and rather exciting. And one of the things we'll do in a moment is try and understand what that means. Well, I already sort of told you what that ends up controlling, but this is the first time you see it in this sort of story. Again, if you weren't able to do non-perturbative physics, you wouldn't see this. So this shows up in JT supergravity quite naturally, and there's a nice model of it at at small h bar and low energy that I'll talk about in a moment. But I should say that in ordinary JT gravity, with the non-perturbative definition that I give for it, you also have this rho of zero at E equals zero. And so this is something that it would be nice to study. And there's a spectral form factor you can also compute, and ask, well, what does it do for us? So that leads me to the last section. Spell physics correctly, Clifford. What is the physics of this rho of zero, and how do I get at it? And indeed, you might go on general grounds. This is interesting. It reminds you of having some degeneracy of ground states in some system. It might remind you of discussions of spin glasses, etc. And I should also point out at this point, there's a lovely paper by Netta Englert that I think she talked about in this series not so long ago with Sebastian Fischetti and Alex Maloney about trying to do JT gravity and see if there's some sort of spin glass-like phase by studying the free energy using replicas. What I'm able to do here is study the free energy in this regime in the aforementioned ultra low temperature limit, where I can get at some of this quite nicely. First of all, rho of zero in that limit can be computed analytically, because there is an exact model. And the exact model is essentially that Bessel function sector that I was telling you about. Remember, I said that so you have this sort of behavior for the potential, and at very low energies, these wave functions actually turn out to be Bessel functions. So it's so in that regime, then I don't need the numerics I was talking about. I can actually solve for these psi's explicitly, and thus do all the sums and all the integrals I need to do in order to do the replica trick in this matrix model language. And the point is this, because the potential essentially becomes just a 1 over x squared type potential in this regime, and the Schrodinger equation, essentially after change of variables, is basically Bessel's equation, as I observed many years ago in some papers from the mid 2000s. So I can actually write down the Bessel functions and do this computation and analogs thereof that I need to do in order to compute. You notice in that limit, actually, so this is a small h bar and small energy limit. You notice that I can actually just read off what this rho is because I can compute it exactly. And it turns out to be, well, something I can compute exactly. It's a quarter mu squared over h bar squared. Some number, some intrinsically non-perturbative quantity. And then I can go ahead and do the replica trick. So I've essentially given you all the tools that I need to do. The replica trick involves trying to take, trying to extract the beta dependence I want for the free energy from something like this, where I want to get the average of the log, not the log of the average, but I can compute in terms of the powers of the average of z to the n. I can compute powers of z to the n using the techniques that I was telling you about, and I can explicitly do those projection integrals and all those things, those nested projection integrals and all those types of things. I can do that all because everything is written explicitly in terms of Bessel functions, which I can then in turn expand in this low energy regime. And so this is what I was telling you before. And so you actually then just get out the dependence. Now you have to regulate the result carefully by making sure that when you do the projector integral, you're getting something finite in the beta dependence. So there's a few words about that in the paper explaining why that's quite reasonable from the undouble scaled matrix model perspective. And just for the sake of completeness, I can also add in a piece that corresponds to the extremal entropy, and it's natural to see how that also comes out of the log n dependence of this integral as well. So I essentially get this for the free energy, and then finally, then I have all I need to compute the full thermodynamics, and that was what I wrote in the terms that I wrote in that earlier slide. Now, because I know what rho 0 is in terms of the Bessel function limit for the spectrum, I can also just ask, what is the first peak? Turns out to be, after I take a derivative, it's the location of the first 0 of J1, the Bessel function J1, as a function of energy over h bar. And so I can read that off, and I see that function I had, mu over h bar, mu squared over h bar squared, a quarter, is essentially telling me that it's this energy gap up to a number of order few. And so I have this lovely result, as I was telling you, then, that I've in some sense, from first principles, shown you how the energy gap, or the average energy gap of the black hole spectrum, controls the low temperature, or in this case, the ultra low temperature physics, temperatures exponentially small, as opposed to the usual semi-classical discussion where the temperature is of order 1. Temperatures exponentially small where I'm seeing the discreteness of the black hole spectrum. So that's the free energy calculation. Okay, I've talked about a lot of things. It is well beyond the 130 that I promised, but I hope I hope that was useful. Let me summarize briefly. Some of the questions that I've already had anticipate some of the things in the summary, so I can go quickly. I have various JT gravity theories. Let me also mention the fact that there's many authors now working in terms of either Liouville theory or minimal string theory models, mostly on the perturbative side, discussing JT gravity in those terms. My work here has been mostly focused on the non-perturbative physics. And the key message is that it isn't formal to describe this in terms of an infinite number of minimal models. I can explicitly get results. I've shown you some. And yes, there's nothing special about this particular set of TKs. It is clear that being able to, that the existence of the matrix models and the existence of the non-perturbative solutions that I can build in this way tell you that there is non-perturbative physics for other things that deserve to be called JT gravities many of them should be thought of as deformation of the JT gravities we know and love. It just amounts to changing the TK recipe in the appropriate way. So I should say, look out for some nice, I hope you agree, results by myself and my student, Felipe Rousseau, to come soon. And I'll stop there.
Questions for Clifford?
I just had a general question. In the all of these things that you're doing from the kind of matrix model side, when we're talking about non-perturbative things here, I'm a little bit unsure about how that relates to the sort of non-perturbative in the sense of summing over all these different genus pictures that you had
Yes.
in the beginning of the talk. Maybe you can just comment on that.
That's a great question, and I went a little fast on that. Let me see if I can scribble in some blank space here and make that a little clearer. Oh, actually, I think I included some. Hang on. Yes, I included some blank slides. There's two. It's actually very very subtle. There's two places that the non-perturbative physics comes from. Well, let me say there's two places where the perturbative expansion comes from. Remember, the expansion parameter is h bar here, e to the minus s naught. Where does this come from? This comes from the fact that I have an s naught multiplying the Einstein-Hilbert action. And so in the gravity theory, I have a weighting of the action that looks sorry, there's some sound issues. Okay, good. I have a weighting of the action that looks like this, coming on the gravity side. And so indeed, so first of all, we could ask where's the perturbative expansion in H bar coming from on this matrix model side? And then any corrections we get that are non-perturbative should then also have some natural home in this language. And in this language, we should basically ask for anything that corresponds to physics which involves this expansion parameter, but may be smaller or not able to be captured in a power series in H bar. I'm just going to call H non-perturbative physics. And so that includes instanton type effects where I have, say, e to the minus thing over H bar, the classic instanton type effects that we might get, which you could then think of as instanton effects from the point of view of the gravitational the gravity saddle and so on and so forth. So I can look for the same kinds of effects over in the matrix model. But where are they in the matrix model, you get to ask. And as I said, they are in two places. Oops. They're in two places. One, there's the correction to the potential itself. So there's what I was calling U0 of x, and that gets corrected to U of x. So that includes effects that come as follows. Essentially, I have an ordinary differential equation that the matrix model supplies for me, and it has some. For example, so it has u to some power. Say the simplest non-trivial one would be, say, u squared equals minus x, and then there's some maybe u double primed and u primed u's and other pieces like that. Right, make the nonlinear equation. These have powers of h bar in front of them, h bar squared, h bar, etc. At leading order, then, that leading piece of u is controlled just by solving this polynomial equation. But then I can essentially perturbatively, I can say u is equal to u0 plus corrections, and simply substitute them back into the equation and develop a perturbation theory at leading order. And so I'll get a correction at order h bar squared, h bar squared, etc. So that's one class of corrections, and I hope I'm answering the right question. which sort of smooths this thing out into something other than just the solution of this equation. But then also I have corrections to the fact that I have the quantum mechanics problem on this potential, and I can also look at given a wave function psi of x in this background, I can expand that thing as a function of h bar as well, and pick out the perturbative and instanton and beyond type corrections to that. So all of those kinds of things contribute to the kinds of beyond perturbation theory type physics that then I interpret on the gravity side as stuff that I can't see in perturbation theory. I hope that answers the question.
I think so, sure.
Okay, good. Yeah.
Could I ask about the low temperature results?
Oh, yes.
So there was, in this paper by Netta and friends, they speculated that there was some kind of replica symmetry breaking going on. I know you mentioned that at low temperatures, the non-perturbative effects are very important. Is there a way to understand kind of a replica symmetry breaking in the replica trick from your results?
So good question. I've been thinking about this, and I had some lovely conversations with Netta et al. Where we were trying to understand, where we are in respective pieces of parameter space, as it were. So there's some general remarks to be made, but let me say the following. I think they were anticipating replica symmetry breaking by using the techniques that they could use, which is on the gravity side. They had to make, I think, certain simplifying assumptions about. They knew that non-perturbative physics should be important, but it's very difficult to characterize it using just the gravity side. So I would say that at least in the regime I'm working in, I can see that the non-perturbative physics is organized because, in some sense, the matrix model is smarter than all of us, is organized in this rather beautiful way where the dominant wormhole contribution is democratic in all of the boundaries in some sense, and so that's sort of so it doesn't, there is no replica symmetry breaking. It's possible then, as you come away from that limit that I'm working in, it's possible, and I had this picture where maybe those other contributors to z to the n that I was talking about. Remember, there's that leading piece that looks like a z of n beta that in some sense is saying all of the boundaries are on the same footing. But then there are other pieces where there's e to the minus beta h and some projector and various of them with sprinklings of projectors in different ways. They're all contributing to the connected wormhole, but in some ways they treat clusters of boundaries in different ways, at least sort of structurally how they look. And I wonder whether there's some sense in which those are some sort of natural patterns of replica symmetry breaking as you come away from the ultra low T and H bar limit. I don't know. And so maybe that could make contact with some of the things that Netta et al. Were thinking about. I'm not sure. I should say, though, that it is common, as they do, to say non-perturbative effects are instanton effects, just e to the minus 1 over g effects, and you're good to go. And non-perturbative effects are much more than that, as we've seen in some of these precise models. And so I think we need to be a little bit more careful about how we anticipate what non-perturbative effects can do when we're coming from the side where maybe we don't have a natural non-perturbative formulation. And so I think the matrix models might be teaching us language that we can later on go back into the gravity side and be a little bit richer in terms of the kinds of non-perturbative physics we see organizing the physics in crucial regimes. There's a lot to be done. My feeling then is that there's, in the sort of parameter space, roughly speaking, of temperature, you got T equals 0 there. There's some ultra low, exponentially small regime where I am, where there is no replica symmetry breaking, and I do wonder if there's some sort of intermediate regime where Englert, Fischetti, and Maloney are, which is there, where maybe there are some non-trivial things going on. Maybe there is some non-trivial phase structure there. Maybe there is a spin glass phase. I don't know, but it's certainly much simpler once you get down here, and the non-perturbative effects show you how to do that.
I see. Thanks.
There's some numerical studies in SYK in the very low temperature regime to see whether there's replica symmetry breaking or not. I don't know if they're conclusive, but yeah.
Yeah, there's a number of papers. I'm confused about the literature.
Yeah, me too.
And also, again, I don't have a good sense of how their temperature translates into the temperatures here. You know, it took me a while to fully appreciate. You know, this is with discussions with people like with Edward and Ed Witten and Juan Maldacena, where I was sort of trying to explain their results. It took me a while to properly appreciate that even though we're all at low temperature, you know, you can still be widely separated in terms of the regimes that you're interested in, and in some sense, I'm sensitive to, like I said, exponentially. You know, I'm able to see the discreteness of the spectrum, which is controlled by this stuff, and so I'm exponentially small. I don't know if those numerical studies of SYK are really talking about that, or whether they're back up here. So there's work to be done.
Yeah. I think we're both starting to teach in 10 minutes, but I have a quick question.
Yeah.
So in the old days, this expansion was interpreted as a sort of a worldsheet for increasingly complicated topologies. The interpretation here is different. I'm a little bit confused because those models are so closely related. How you can have different interpretation? Like, what is this sum over topologies? Is it a string worldsheet? Is it sum over space-time topologies? It seems to me like because these models are basically deformation of each other, you have to choose.
I think that they are. I think it's perfectly fine to use the same language that we used in the old days, which is that they are sums over surfaces of different topology. But it's also, I think, some of these modern discussions we've been having about averaging and stuff like that. I think it's all true, and in some ways, there are concepts that we had from the old days that match quite naturally here as well, in the sense that we have to remember what we're computing, right? And what kinds of questions we're asking. And I think we've been asking certain questions where this sort of averaging picture is indeed quite natural. And they're very different from the sorts of questions that we got used to asking in modern terms when we're doing things like ADS-CFT, etc., where we have some fixed geometry, we have some fixed black hole, and we go, oh yeah, it's Yang-Mills at finite temperature, and this is the background, what have you. And I think we simply weren't asking about sort of ensembles of that, of the spectrum of that black hole and stuff like that. We could have, but we didn't know how to compute. The matrix model language, on the other hand, is very good at computing that sort of thing. And so the matrix model then naturally says, hold this fixed, and sure, ask about a geometry like that. But actually what the matrix model does, it tells you how to sum over all possible things that have that asymptote and that topology, and then do it for other topologies as well. And so that's in some sense why it's giving you, at least in my opinion, that's why it's completely natural. And from a 1990s perspective, not at all surprising that you're getting an averaging, because it's an ensemble average, right? It's Wigner. This is what Wigner is telling us to do. But now we're seeing it's capturing a sum over random surfaces. So quantum gravity in this two-dimensional sense, where I mean quantum gravity to mean I fix, for example, these boundary quantities and I sum over everything that can happen fully honestly in the way we're supposed to do in quantum gravity, is indeed then giving us some sort of ensemble average if we interpret it in terms of some one-dimensional theory that we've held fixed. And that's great. How that generalizes to higher dimensions and so on and so forth, I don't know. But I would say at least this interpretation of averaging, and there are other sort of adjacent averaging discussions as well that aren't all like this, but at least this particular aspect of the averaging, this aspect where I'm talking, for example, about averaging over the parent black hole spectrum, I think that's all very, very natural from the old matrix model perspective. I don't need new words. It's the old words said now with feeling. We've found something. In some ways, we've found a lot of that averaging story that went back to Wigner. In some ways, when we were doing the string theory stuff in the early 90s, we kind of didn't, the Wigner motivation wasn't as strong. We were using more the 't Hooft motivation.
Right.
And in some ways, we're now revisiting them again, maybe for the third or fourth time. But now we're bringing back the Wigner way of thinking about why we're doing this. And so in some ways, we go all the way back to Wigner. There's that averaging that we're all excited about now, at least in this limited sense. That's how I think about it.
Good. Yeah, I wish I could talk more. It's 5 minutes to 2,
Yeah.
so we both have to run.
Yeah.
Really great talk. Thank you.
Oh, thank you. Good to talk to everyone, and hope to see you all soon, either online or in the real world somewhere, sometime.
Thanks, Clifford. Very nice.
Thanks, Clifford.
Thanks. Bye.